Hello, my name is Jacob Parrott. I will be giving my presentation for Project 2 for ME597, Decision Making and Engineering Design for the fall of 2001. This project is reviewing several papers written on customer choice modeling for engineering design. First, I'd like to do a safety share. If caught in high winds, the safest place to be obviously is indoors. If you are stuck outside in high winds, make sure that you take cover next to a sturdy building or under a sturdy shelter. Stand clear of roadways or train tracks, and use handrails when available, and avoid elevated areas. Obviously watch for flying debris. If you're driving, make sure you keep both hands on the wheels, watch for flying objects, keep a safe distance from other vehicles, and if it's just too windy, pull over. Find a safe place to pull over, away from tall objects or trees or anything that could fall and hit you. So let's continue with the meat of the report. So this project, I'm reviewing 3 papers, technical papers, and I'll be giving a brief summary on what the researchers were presenting in these papers and a little bit of my findings. So, first paper that I am reviewing is called Modeling Customer Preferences Using Multi-Dimensional Network Analysis in Engineering Design. Now this paper is by Mijin Wang, Wang Chen, Yang Hong, Nishir S. Contractor, and Yang Fu. I apologize to those people who are mispronouncing their names. Now, this paper discusses the framework of using a new multidimensional network analysis in engineering design. It does not, well, I should say further work is needed to conduct actual testing on this model. So that in mind, why are the researchers presenting this new method? And because the reason is because most of the existing models or applications of network analysis are unimodal or unidimensional. They contain a single class of nodes. So you can kind of see here, they have listed 3 different types of networks that are typically used. Unidimensional networks, there's only product associations. You don't have any human or social economic interactions between the nodes. There's a second method, this bipartite method, where both human and product elements are implemented, but you don't get any interaction between the nodes, just between the nodes of the same element, just different sets are allowed. So they're proposing a multi-dimensional approach which allows these interactions between all the nodes, and this should give a better representation, including the social economic interactions. So, the multi-dimensional customer product network is a way to network modeling of customer to product relationships. There are 2 types of nodes in this framework: product nodes and customer nodes. These are shown by these 2 layers. The product layer holds a collection of engineering products, and the customer layer holds or describes the social network between the customers. If there's any interaction between the customers, the relationships or influences between those customers. Now, 3 features are used to analyze the customer-driven product associations. There's centrality, community, and hierarchy. Centrality is basically a collection of the most competitive products in the network. Community is the number of groups of nodes that were internally connected. And a hierarchy is a strict, partially ordered set represented as a directed network. Now, how do they show the links between these? They calculate the lift. Now the lift is the strength or the interaction between two nodes. So basically in this case, this reflects how often two products are compared by the customer population. So if a product is compared more often than another, that lift is going to be higher for the one product compared to the other. There's two different networks. They give a lift for an undirected network and a directed network. A directed network also includes the purchase data of the customer, not just the two product interactions. Now, the advantages of this MCPN are that you can easily figure out what a customer is willing to choose based on the various social influences. However, a huge drawback with it is it gets very complicated very quickly. As you can see in this diagram that they posted, this is just the product relations only. Then you add in the preference links, it gets a little bit more complicated. But then when you add the social relations, it's a mess. So that is why they want to do more work on developing this network. It's a very interesting paper. Really, really cool. Second paper that I chose is called A Data-Driven Network Analysis Approach to Predicting Customer Choice Sets for Choice Modeling in Engineering Design. Now, this paper discusses an approach to gather existing data of choice sets, and then from this data forecast heterogeneous choice sets for an individual customer when data is deficient. So what's being addressed here is that most often choice set information isn't available in traditional data from the market. And this leads to misspecification when predicting choice sets. Now, the paper goes into detail on how they are able to predict these choice sets. So first, they also use a lift calculation to determine the connection between the two products. They also further develop this lift where they're only considering the significantly positive lifts. If it's not significantly, if it's a negative lift, they'll consider it zero. Now, using this lift, they can utilize the Newman's optimal modularity method to find communities. This is the calculation where they find the weighted links between the communities, or the difference between the weighted links between the communities. Now, this is an example of a network and the product communities within that network. Now, these links are obviously the lifts, and the numbers there are the lift values. So the higher the number, the stronger the link. Now, the green nodes are one community. That's, in this example, a small compact vehicles. The red nodes are another community, and those are, in this example, mid-sized vehicles. Now you can see the link values. There's a couple outlier nodes. This is a typical vehicle association network. Now, once they find those community and lift values for that, they can overcome limitations imposed by the customer heterogeneity on a sample choice set predictions, and the relative consideration frequency can be calculated. Once they calculate this relative consideration frequency, they need to further define this because it doesn't consider product co-occurrence within a community. So they define the co-consideration frequency, and that is this equation. Furthermore, they can next develop the customer-specific product consideration probability, and in all of that, these equations don't take into account the situation where purchase choice, say K, is an isolated node like we saw in that previous slide. So this equation takes into account if that happens within the product network. Now, Now, 2 case studies were presented during this paper. They chose in the first case study to use synthetic data, and then the second case study to use real-world actual data. In this case, they took from the automobile industry. So for the first case study using synthetic data, the goal was to try and find if this method had any significant bias. So 4 models were used to illustrate the accuracy of predicted choice. There was a true choice set, which is the actual data being compared. The second one was a universal choice set. The third was a random choice set. And then the fourth is the predicted choice set, which this paper is about. Now, to find the error between these, the mean absolute percentage error was calculated for each model. And as you can see, the predicted choice set is the model that is closest to using the actual data, the true choice set. So this shows that the predicted choice set is a good model to use. Now, the second case study used actual data from the automobile industry. Now, this data was generated from 2 sources, a J.D. Power Vehicle Survey and the National Household Travel Survey. Researchers had to test the network associations and optimized these using apologize for mispronouncing this, Futurman and Rheingold algorithm, which you can see here. The Futurman, and Rheingold algorithm is used to in a visually appealing way. Now, here are the results from case study 2. 3 models were used. One that had a universal choice set, one that had randomly sampled choice sets, and then the last was with the predicted choice set, which the paper is discussing. Now, after all these calculations, the estimated coefficients derived in models 1 and 2 end up looking very similar. The model using the predicted choice set ends up having the best fit, the highest fit, which has the coefficient estimates different than that of the first 2 models. It was determined that the predictive choice set produced choice models provide a very promising option for design engineers to use while modeling a decision problem. Now, moving on to the last paper discussed. This paper is actually a chapter from the book Decision-Based Design, Integrating Consumer Preferences into Engineering Design. I chose to look at chapter 5, which is Product Attribute Function Deployment for Attribute Identification, Concept Selection, and Target Setting. Now, this chapter discusses a different approach than the traditional quality function development, QFD, which was used in a couple of the previous papers that I just went through. This new method is called the Product Attribute Function Deployment Method, or PAFD. PAFD uses multiple steps to map out the qualitative attributes for helping to establish the engineering priorities. Now, why to use PAFD instead of QFD? Well, PAFD was used to extend the qualitative matrix ideas of QFD, while also using a quantitative process of decision-based design. Now, we have to look at QFD. QFD was designed to bring together marketing data and engineering data and use a simple qualitative analysis. It uses the house of quality to illustrate the mapping of engineering attributes to customer desires. Now, there are limitations to QFD though. First limitation is that it only uses customer and competitor information to set targets. It does not take into consideration other attributes like market share or potential profit. This lack of inclusion of such elements can lead to QFD setting targets that can't be achieved. Also, QFD assumes that every customer preference is the same, so that it can be characterized by a group utility function. This isn't really the case in real life setting. Individual customers have individual, unique preferences that should be modeled as such. And finally, QFD is biased in its results to meeting any customer requirements. So, to help overcome these requirements, the authors present the PAFD method. The PAFD method uses two houses to help establish the goals. So, in the first house, it is used for mapping the relationship between the engineering design attributes and the customer desired product attributes. It's broken up into three sections. The first section contains the relationship matrix of the customer desired attributes to the engineering design attributes. The second section contains another relationship matrix of the interactions between the customer demographic attributes and the customer desired product attributes. And the third section contains a table that shows the tabulation of the competitive alternatives with the engineering design attributes resulting from the customer desired product attributes, as well as the price and the engineering targets. The purpose of establishing this house is to ensure that each customer desired product attribute has a corresponding engineering design attribute resulting from the customer's desired attribute as a vector. Also, that the interrelationships between these and the customer demographic attributes are very clear. Now, once this house is tabulated and the targets are determined in this house, we can then move on to the second house. This is to characterize the design. Now, here, using these engineering attributes developed from the first house, we also take into account design attributes from corporate requirements, regulatory requirements, and physical requirements. With these four sets of attributes, all the design requirements will be considered to achieve the best decision possible. Now, the engineering attributes are mapped with design features. And also, this is where you can list as many design concepts as you want. In this case, there's 2 design concepts. We could have 3, 4, 7, whatever is being considered. The mapping between these attributes and design features leads one to figure out manufacturing attributes and estimate manufacturing costs from those. So, the paper then presents a case study, and the case study first presents the QFD method, and then they present the PAFD method. So this case study presented has to do with the design of an automotive pressure sensor. They call the manifold absolute pressure sensor, or MAP. So first, the QFD method was presented. Now, QFD method uses a house similar to the PFD method. It uses customer attributes and engineering attributes. It also takes into account a survey of customer ratings between different models. So in this case, this is the sensor that is ours, and then there's competitor models here. So the survey asks customers, which model of sensor is the best? And you can see the highest and the lowest. And from there, you can determine a target on which engineering attributes to pursue. In this case, it was decided that the new sensor should have improved target performances for accuracy, pressure span, temperature range. Since these have high technical performance, and the sensor that is theirs is not considered market leading. It was also decided to improve the target for connector mating force because it has a low technical difficulty and is easy to achieve. It was decided not to improve the target for housing ferment, since, as you can see here, the sensor, our sensor is what they call it, is the market leader. So that's the QFD method. From there, from those targets, you can then proceed to go on to further engineering design concept analysis. So next, the PAFD method. First house is listed the same customer-driven attributes as in the QFD, and then also the engineering attributes to be considered. This is mapped out along with the demographics, and targets are established. From these targets, we can then plug them in to our second house, where we are considering they are considering two design concepts. These concepts of the sensor are a piezo-resistive and a capacitive sensor. Now, the design features for each sensor are slightly different because there's different models, but the engineering attributes are the same. So these are all mapped. Manufacturing attributes are then determined, and then the costs are estimated based on all this information. Now the results of this case study. Now just looking at the PAFD model, if you were a risk averse, a risk neutral, or a slightly risk prone person, you would choose the first concept, the piezo-resistive design. You can determine that based on this utility chart here. The dark line is the piezo-resistive design, and the dashed line is the capacitive design. Now, as you can see, as you go up more risk averse, then the dotted line goes above the solid line here. Now, comparing the QFD results to the PFD results, they show, if you look down here, they approach this design from a moderately risk-averse person as the decision maker. The piezo-resistive concept from the PFD results has the highest utility of the three. It's at 1.7 million. The second design concept is 1.4 million, and the QFD results give a utility of only 170,000. Now, why is the QFD result so low? The utility of the QFD model is significantly lower than that of the PFD results because the QFD is biased towards meeting the customer's product desires and doesn't consider the cost of those desires. So as you can see, the cost up here per unit is a lot higher in the QFD than it is for the PAFD. So as you go down the table and multiply out and calculate the utility, that's why the utility is so much lower for the QFD than the PFD. And thus the reason why the PFD method is a more accurate way to choose than the QFD. So thanks for listening to my summarization of these three papers based on the customer choice modeling for engineering design. I enjoyed this project very much, and I look forward to learning more in the future. I hope you enjoyed. Thank you very much.